opcodes or the custom?
Reserved. Custom cannot be broken. Custom is something that has been frozen. That these opcode spaces can never be used by the foundation to define any new extension that is meant for customer usage to define whatever the customers want. So all the
So the ratified ones go into the
yeah,
reserved.
yeah.
So may I ask a doubt?
Yes, please.
You were talking about fence, such as
Yeah,
Zenfisi.
yeah.
So you said that these are used for self-learning or self-implementing code, self-changing code.
Mhm.
Could you elaborate a little more on how you can implement self-mutating code via Zenfisi?
So, Java or just-in-time compilers, these are all self-modifying codes. Basically, you have a piece of software which creates the next set of programs that you need to execute, right? Or it creates the instructions, or it tells you, it copies a piece of data and overwrites a piece of instruction sequence and says you need to fetch here again, right? For example, you would have a fence, you would have a function which is performing an add operation or matrix add operation in software. Now, what you do is in the same location where this matrix add was, you go and repopulate that same place with a matrix multiply operation. Now, the address is the same. It's just that you have now changed the instruction sequences over there. So these are just-in-time compilers, JIT in some sense, where you have this feature that on the basis of the data flow, I will choose what to execute, and I will dynamically generate those set of programs, or I will dynamically populate those instruction sequences. So when I have to dynamically populate, I can only do that through store operations, right? That's the only way that I can write or update memory. If I have a cache, then all those writes will be stuck at the cache. These are write back caches. So and there is no internal synchronization between an iCache and a Dcache, right? If an iCache miss, or if iCache already has the data, it is not going to request anyone else. So that's why we use a FENSI, where we say that once I have completed my store operation of writing the new set of instructions, a lot of these may already be present inside the cache. So I need to first flush the data cache so that all of these data are now visible to the main memory. Then I tell the instruction cache that you got to forget whatever you've cached, you got to empty yourself out. There's no empty yourself in iCache, you just have to drop everything, right? There's no write back in instruction caches. And then it starts fetching. And when it starts fetching, it reads the updated value in memory. So that's how self-modifying codes will use ifNSI to maintain synchronization.
Thank you, sir.
I have a little off question. So yeah, similar lines. So, is that same mechanism used by compiler to generate instructions? Or like, I mean, like how does the instructions actually get
static, right?
Sorry,
Compiler
can
is
you repeat?
offline, no? You compile something and then you give it to the processor to execute. Just in time
Okay, so
dynamic. Your one program which is already running on the core is creating another program. Compiler is different, right? You compile the code on your host and then you offload it to your processor to execute.
yes, sir. So like it is stored in memory, and like how does is there some kind of special memory like where all the instructions are like stored?
No. This is all flat memory systems, right? It depends on your operating systems. You can have text regions, data regions, read-only data regions, and whatever. But you are confusing two different things of static compilation versus dynamic compilation. The classical way of what you do today, you compile a piece of code and then you say /a.out, right? That is static. You've written a program and you're executing that program. In dynamic, what happens is you've compiled one program and you're executing it. While execution, you've created a new program somewhere. As soon as the first program finishes, it starts executing the next program. So the next program was not compiled by our original compiler. It was generated using the first program's execution itself. And that program would have either modified itself or it would have modified some other regions of the instructions.
Oh, okay.
So in memory, there is no distinction of instruction memory and data memory. This is all based on your paging mechanisms and permissions and all that. In hardware, we don't distinguish between instruction memory and data memory. We have instruction cache and data cache, but when it comes to main memory, it's just a flat monolith.
So when we do the /out, so actually what we are doing is we are setting some, we are moving the instruction pointer to that particular of instructions.
Correct.
Oh, okay. Thanks.
Any more questions? Okay, so since we have just 1 or 60 to 90 more minutes left, I will be covering the microarchitecture. I will be skipping the privilege spec because the privilege spec is a little more involved. You might not have enough takeaways at this point from the privilege spec, right? So I would rather walk through, do a walkthrough of the core microarchitecture because that's something that's not easily available. The privilege spec, on the other hand, is extremely well documented in the spec itself. So that's a good resource for you to read and come up to speed. So I believe the microarchitecture session, which this slot is supposed to have, we'll cover that. The privilege spec, if you have any questions, you can reach out to me at any point, and I'll be happy to resolve or answer your queries on that. Okay, so start sharing. Okay, so what we're going to do now in the next 1 hour is we're going to do a microarchitecture walkthrough of what we call the Chromite Core. The Chromite Core is basically an open source RISC-V core that we built at Encore. This is based out of the Shakti processor called the C class, right? So if you've heard about the Swadeshi processor challenge, which ended last month in December, it was a 15-month grand challenge that the government organized, where people were expected to use these processors, use the Shakti C class or other processors from Shakti and build applications and build an end user product using these processors, right? So the process that was used there, one of them was called the C class, which is what Encore has based its own implementation of Chromite on. Chromite is basically a 6-stage in-order core. It is completely open source. It's under the BSD license. What BSD stands for is you can use this core, you can make money out of this core, you can change this core, you can brand it as your own core, and you don't have to tell us, right? We don't take liability for the core as well. So that's the other side. This is designed in a language called BlueSpec System Verilog. We've not used conventional mechanisms of conventional languages like Verilog or VHDL, which are too low level and have a huge design cycle. But with languages like BlueSpec System Verilog or Chisel, you get a sufficient amount of abstraction, which increases your productivity anything between 5 to 8x. And it gives you, more importantly, a very synthesizable code, 100% synthesizable code, which means the BlueSpec code, when compiled, generates Verilog. That Verilog will always be synthesizable. You can always take it to FPGA without having any combinational cycles or race conditions or anything of that sort happening. Chromite is not a single core. It's a core generator in the sense majority and significant aspects of the microarchitecture and the architecture are configurable. You can define the size of the caches, the kind of replacement policies you want, the size of the branch predictors, whether you want a branch predictor, operand forwarding, scoreboarding. Do you want scoreboarding? Do you want to enable write after write scoreboards or not? All those options are available as a configuration. So from the same BlueSpec code line, you can now generate multiple different instances of a 6-stage core with varying performance, area, and power design points. More importantly, while you're able to hit multiple design points. So with the Chromite core, you can generate a very minimal RV32i 5-stage in order core, which is probably 4K LUTs or less, which can only run just machine mode, for example, right? No operating system, just firmware. Whereas from the same code line, you can also generate a completely Linux capable system, which is able to run Linux and operating systems and other Debian based, Ubuntu and all those distributions as well, right? This all comes from the same code base. And by maintaining the same code base or having a code generator like this, verification becomes easy because even though you can generate multiple instances, if you verify the original code base, you don't have to verify each of these new instances again, right? It's an extremely modular design. With BlueSpec, we've made sure that the boundaries are allow the modules to be plug and play. I can add new computational units. I can add new types of caches. I can add new types of branch predictors without having to screw up the rest of the pipeline. That's the link, chromite.readthedocs.io. This is where you'll find documentation about how do you clone it, how do you run simulations, how do you benchmark it, how do you run hello world, the microarchitecture, all details that I'll be talking to you is all present in this documentation in detail. Today, the performance of the Chromite core is 1.78 dNOPS. This is using the latest GCC 11, and the core marks is 3.8. This is extremely competitive to equivalent ARM cores, as well as other RISC-V cores, which in this particular design space of a single order Linux capable system. If you have an FPGA, a 100T, an RT100T board with you, which is around $100, we have also given you a template SoC, which has UARTs, peripherals, GPIOs, SPI modules, I2Cs, all of those available, and you can boot Linux, you can boot operating systems like Zephyr, as well, real-time operating systems. And the documentation of which is available at the bottom, chromite m-soc.readthedocs.io. So all the steps, right from cloning the repositories, generating the Verilog, synthesizing it on Vivado, and burning it on your FPGA, connecting an OpenOCD, connecting a debugger, all those steps, all those documentations are available on this particular website. Right. Also, Chromite is not a physical chip. Please understand that these are all soft IPs. These all exist as hardware design language, HDL codes. You can take this code, generate the Verilog, put the Verilog in an SoC, take that SoC through your physical design flow, synthesis, floor planning, place and route, clock tree synthesis, blah, 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 all the way to GDS2. The Chromite core is not a chip in itself, but is one of the major components that goes into a chip. Right, I hope that's clear. Any questions so far?
Has a chip been made?
Yes, we've manufactured this twice. In fact, there is one more tape out that's going to happen in a couple of months. So we've tried it out on Intel 22 nanometers in 2017. We've also tried it in Chandigarh at 180 nanometers. We will be doing another 180 nanometer run in the next month. So yes, an instance of this core, a 64-bit instance with Linux capable, which is what had been taped out, has been done.
Okay.
So we can use this to create a processor architecture which will boot Linux or maybe any real-time operating system. Is that so?
Yes. So the core is just the core. For any product or any application, you need an SoC, which has other set of components, right? You need RAMs, you need a DDR memory, you need flash memories, you need GPIOs, you need serial protocols like SPI, I2C, all those things. So you need to build an SoC, which has DMA and security, USB, DDR, PCI, whatever you want to boot. You connect all of them along with the core, build an SoC, and then you manufacture it.
Okay, so all those peripherals are also included here.
We don't have the high-end peripherals like DDR, SO5, PCI and stuff. But what we do is for the FPGA, this is a Xilinx-based FPGA. So Xilinx provide a lot of these IPs themselves. So we simply connect them at the SoC level. So we've taken the USB, Ethernet, DDR IPs from Xilinx, which are all freely available if you have the board with you. And we have given you an SoC which allows you to integrate all of these components and boot them on an FPGA.
And is it possible to have our own implementations working along with the core? Like I create a small UART.
Yeah, absolutely. So the SoC is all integrated at the Verilog level. We have an interconnect AXI4, APB, AHP. You can bring any of those connections outside. And at the Verilog level, you can connect your UART to any of those peripheral interconnects.
Okay.
Okay. So this is the overall microarchitecture of the Chromite Core. This is a 6-stage in-order processor, right? So your typical 5 stages, that's the fetch, decode, execute, memory, and write back. We have an additional stage, which is a PC gen stage, which is where we have the branch predictor and whose primary function is to generate the next program counter, which your fetch stage will process. Right. So we will be going through each of these stages in detail over the next 1 hour. So we start with the PC Gen unit. So as you can see the diagram on the right, there are 4 places that the PC can be modified. PC stands for program counter. It basically tells you where to fetch the next instruction from. Right. So assume you don't have compressed, in which case you simply have to keep incrementing PC plus 4, PC plus 4, PC plus 4, and so on. Right. So that's your regular default operation. So you start at reset, the PC has some reset value, and from there you just simply get the first instruction, then you increment by 4, get the next instruction, increment by 4, and so on. Now there is a possibility that you faced a branch instruction which is taken, right? So what happens is, instead of doing PC plus 4, you now have to go to PC plus immediate value of that branch instruction that we just saw. In Chromite, the branch instructions are resolved in the execute stage, right? And once the execute stage says, hey, you got to change your PC to this, it's been taken, so this is the new PC. At which point, instead of doing PC plus 4, you will jump to this particular PC that is pointed by a branch resolution unit. You can also have traps and redirections. For example, misaligned accesses, misaligned exceptions, page faults. All of these are called traps. Traps will be taken from the write back stage. Right? So when an instruction is executing or when it's decoded, it could have led to any one of these numerous exceptions that the RISC-V defines. If that happens on a trap, you need to jump to a trap handler, right? And the address of the trap handler is present with the CSR. There is one CSR called the trap vector, which will tell you what the trap handler's address is. That is where you need to jump if there is a trap that is taken. So that's the third source of a new PC. The fourth source is the branch predictor. So we have a branch predictor in place. It takes the current PC, It predicts whether this PC was, it first checks whether this PC was actually a branch instruction earlier, and if it was, whether the PC was taken, in the sense whether the branch was taken, and what was the target address it jumped to, right? So if the branch predictor can indicate with a high amount of confidence as to, hey, your PC current value is 1000, but the next one has to be 2000, it should not be 1004, then that becomes your new PC, right? So those are the four sources of the program counter. You either have the branch predictor, or a redirection happening because of traps, or you simply increment by 4 in the default case, or there is a control instruction redirection happening from the execute stage.
What was the ISB again?
ISBs are interstage buffers. Between two pipeline stages, you're going to have pipeline buffers, right? So all of these vertical lines, they basically are flip-flops which will store the result of the previous stage so that the next stage can operate on them, right? We call them as interstage buffers, ISBs. So once a new PC has been generated, you send it to the cache, that is the instruction memory subsystem, and you also send it to the fetch unit. That's the stage 1. Now, in our implementation, we've made slight assumptions. We've always we made the assumption here that the instruction memory is always going to expect a 4-byte boundary address, right? The address is always aligned to 4 bytes. So when you have compressed enabled, there are two changes that can happen. One, you need not always increment by 4. Sorry, your branch predictor may cause a jump to a 2-byte boundary, or the control instruction can cause a jump to a 2-byte boundary, right? But the instruction memory is always given a 4-byte aligned address. Even though you have a compressed instruction and your current PC is, let's say, 2, the address you send to the memory subsystem is going to be 0. And you're going to tell the memory, give me 4 bytes from 0, which includes the 2 bytes that you're requesting from address 2 as well, right? So this is to make sure that we don't complicate the instruction caches with compressed support. It has its own pros and cons. You do face a little bit of a performance issue there, but it makes the implementation slightly more simple and easy, right? That's why we have this 4-byte boundary constraint. We will now look at branch predictor. So the predictor that is currently present in the Chromite core is the G share, a global share predictor. Does anyone know what a G share is? Or
No, sir.
any other type of branch predictors that you're aware of?
We had 1-bit and 2-bit branch predictors in previous session.
Okay. So let me even go before that. What is a branch predictor? What do you expect it to do?
Predict which branch your code is going to take. So whether you're going to take the true branch or false branch.
Okay. And how does a branch predictor predict? So what is the input to a branch predictor?
Previous occurrences, like whether previously it was true or false, whether it predicted true or false, all of those.
Correct. So the 1-bit and the 2-bit branch predictors that you were talking about. So branch prediction is basically the ability very early in your pipeline. You want to be able to quickly maneuver your PC in the correct direction. And why do you want to do that? Because the penalty of getting the wrong PC in the pipeline is huge, right? Because the resolution happens only in the execute stage, which means if I've predicted wrong, or if I've not predicted at all, I'm going to face at least 2 to 3 cycles of latency before the next correct instruction comes into the pipeline. And all the fetches and the amount of energy and power that I spent in fetching the wrong PC stream is all present in the fetch and decode stage will also have to be dropped. So for both of these reasons, performance and power/energy, it is important that very early in the pipeline, we are able to predict what is the flow of the program counter. One way to do that is through branch prediction. There are usually two types or two categories of branch predictions. You can obviously, if you go more in depth, you can find overlaps in third, fourth, fifth categories. But at a very basic level, you can predict based on two things. One is a local history. If for some reason I'm at PC 1000 and I know that this was a branch instruction, let's say I have some magic component which tells me, hey, this was a branch instruction, and I look at this branch's local history. What was its previous history? How many times was it taken or not taken? Was it previously taken or previously not taken? Or previously 2 times was it taken, not taken, all those things. But only of that particular branch. When I'm predicting this PC 1000, I am looking at the history of that branch alone. That is called a local predictor. The other category is the global predictors. What it says is, I know at PC 1000 is a branch. I'm going to predict based on all the previous branches that happened in the last 10 sequences, or all the last 10 branches that occur. So you're looking at a global view of all branches to predict what the current branch should be. Right? That's why it's called a global predictor. You don't only look at the history of that one branch alone, but you look at what were all the branches before it, whether they were taken, not taken, taken, not taken. And based on that, you will predict whether the current PC should be taken or not. It has been shown that a global predictor performs very well compared to a two-stage predictor. Right? Now, there are cases where a two-stage predictor will obviously, if you write software code in a particular way, the two-stage predictor turns out to be better and the G-share will take slightly performance hit. But in the grand scheme of things, G-share outshines the two-bit or the local predictors sufficiently. The other problem with global predictors is it takes a good amount of time to ramp up, because what it does is it holds something called a history register. Okay. History register basically tells you, let's say the history register is 8 bits wide. It can be any bits wide. Let's assume it's 8 bits wide. What this history register stores is, it stores 1 bit for all the last 8 branches. Right? And each bit, if it is 1, means that particular branch was taken. 0 means it's not taken. So if I have a pattern of 1, 1, 1, 1, 1, 1, 0, it means the last branch was not taken and the 7 branches before that were all taken. Right? Now for this pattern to repeat so that I can predict it correctly again takes a little more time than a local predictor does. Because this pattern to come back, it's a shift register, right? The first branch comes in, I predict, okay, taken, and I put in a 1, or it evaluates to taken. I put in a 1 here, and then I shift it. Then the next branch comes, I put in whether it's taken, not taken, I put a 1 or 0, and then I shift it. So the shift continuously happens. Right? So the history register will continuously shift as and when a branch is encountered. And based on that, you can only get that, you'll have to warm up. The warm up time for a predictor is much higher for G-share. But once it's done, it's very strong and powerful. Okay. Now let's look at the G-share in a little more detail. There are 2 major components, right? There is a BTB and there is a BHT. A BTB is the branch target buffer. What this does is, it basically is indexed using PC. Your current PC, you can index into the BTB. If it is a hit, or if that PC exists in the BTB, that particular entry in the BTB will tell you what is the target address that you should jump to. Right? So if PC is 1000, you index here, and suddenly that entry 1000 is valid. That entry is going to hold the jump address. It's going to say, okay, After 1000, you need to jump to 5000. So that address 5000 will be present in the BT. The BHT is known as the branch history table. This is like your 2-bit saturation counter. It's exactly 2 bits wide, and it's a saturation counter. You can go from 0 to 3. If you increment from 3, it stays at 3. If you decrement from 0, it stays at 0. Right? And 2 and 3 means predicted taken. 0 and 1 means predicted not taken. Right? So that's the state of the branch. How do you index it? You have the history register, which is 8 bits wide. You take the lower 8 bits of the PC. You do a hash function. A hash function is basically a XOR operation of sorts, a very weird XOR operation. There are multiple different types of XOR hash functions that you can use. Right? Anything that gives you an 8-bit output. The idea is the lower 8 bits of the PC can be the same for multiple PCs. Right? If there are 2 PCs which only differ in the upper 20 bits, for both of those PCs, if they're both branches, they will both have the same lower 8 bits, correct? So in order for those 2 PCs to index into different places, we have a hash function. So this basically allows you to map multiple same values of the PC, the lower 8 bits of the PC, to different entries, so that you get unique mappings for every branch. So this hash function acts as the index mechanism. You use these 8 bits, so which means the BHT is now 256 bits entries. And once you index a particular entry, it will tell you whether the branch should be taken or not. Right? Simple? Any confusions, any questions so far?
So why would the low level 8 bits would be similar? Because they are the ones which keep on changing continuously, isn't it? Because PC plus 4 and all.
8 bits is 256, correct? Now, if your program is going to be much longer than 256 bytes, no? Your program will be in MBs. So you assume a PC which is at 1 MB and a PC which is at 2 MB. Okay. The only difference in them is in bits 20 and 21. The lower 19 bits are all same for both of them.
Yes.
So if I pick only the lower 8 bits of the PC of both the PC 1 MB and PC 2 MB, they're going to be the same, right?
Yes.
But I would like both of those PCs, if they're both branches, I would like to maintain a different history entry for both of them. If I directly just use the PC as an index, then both of those entries will end up in the same BHT and they'll keep polluting each other's predictions, right? So by using this hash function, which is a XOR operation between a very simple hash function, is XORing the history register with the PC register, the lower 8 bits.
But what in the case of small systems, like small embedded systems, which don't have much large instructions? I mean, yeah, much large instructions. So they will be jumping to nearby addresses, isn't it? Which will be having much similar lower 8 bytes.
This algorithm will still work, right? The hash function only ensures that similar PCs are end up with at unique places. But if your PC itself is different, the lower 8 bits are different, the hash function will still end up doing a unique mapping, right?
Yeah, yeah.
Okay. So far we've seen what the branch target buffer holds. It holds the address, and history table will hold whether you should be taken or not taken. A value of 2 and above is taken. A value of 1 and below is not taken. And you have a history register. Now, who populates this history register? So let's say on reset, branch prediction is 0, nothing is there. You're just going to say not taken by default. The branch reaches the execute stage and says, oh, I'm supposed to be taken. So it's going to send a signal back from the execution unit. It's going to say, hey, you need to update your history register and put a 1 in that particular bit. Right? So it does a rollback and it says, oh, history is going to be 1 for this particular branch. And along with that, it updates a branch target buffer entry. Right? It says, hey, this is a branch instruction. This is the PC of the branch instruction. And this is the address to which it has jumped. So you allocate an entry in the branch target buffer. Simultaneously, you also increment the saturation counter. Right? You again use the same hash function. You know the history register because you've just populated it. You know the PC of the branch. You perform this hash function. You access the BHT entry and you increment or decrement whether on taken or not. Right? So that's how the basic branch history table will work. Branch G-share predictor will work. Every time there is a new branch which is mispredicted, you will come and update the history register so that the next branch can be correctly predicted. And this continues as long as the mispredictions reduce. When you don't have a misprediction, then the execution unit doesn't do anything. It simply says, oh, you're correct, please go on execution. But only on a misprediction will the execution send a signal saying, hey, you did something wrong. This is what you need to do. This is your new updated history. You need to allocate so-and-so entries in the branch target buffer, so-and-so values in the BHT. Now in Chromite, what we have as a branch target buffer is a fully associative memory, right? It's 32 entries. How you index into a BTB is you compare the upper bits of PC with, you store the PC also in the BTB. You compare them, only one of them will be a hit. When it's a hit, the corresponding entry will tell you the jump address. Very simple.
I have a doubt. So, is there any prediction done for function calls?
We will come to that. So right now for the branches, only for conditional branches, the branch equal to branch less than is what goes into the BHT table and the history register. For the unconditional branches, we do not touch history register or the BHT at all. For unconditional branches, we do it separately. Okay. Because unconditional branches, that is jumps, they don't actually depend on the previous history. They're always taken, right? There's no prediction to be done. You just need to know what is the target address. So for all jumps, we simply assign an entry in BHT and BTB, but we don't update the history register or the BHT for that, because they will always be taken, and you just need to know that this entry is a jump and this is the target address. That's all.
Okay.
So this is the history table. Now, what you must have seen, or I'm not sure what was taught, but a typical conventional saturation counter goes from 0 to 1, 1 to 2, 2 to 3, right? But there is a enhanced transition or an enhanced counter which will give you better results if you go from 0 to 1 and then directly to 3. And if you're at 3, you decrease from 3 to, and again you go to 0, right? So this 1 to 2 and 2 to 1 transition is gone. Basically, you're just going from 1 to 3 and 2 to 0. So this particular state transition gives you better results in terms of predictions. Now for calls and returns, function calls and function returns, they have a property. As soon as you do a function call, if you remember the JAL and the JLR instructions, they store the return address in the RD register, right? So whenever there is a call, you're doing a jump, so you know what the target address is. But you also expect a return to happen very soon, right? So what we do is we maintain a module called the return address stack. As soon as I detect a call, so I have a PC is a function call, has an instruction called a call instruction or a jump instruction, which is interpreted as a call instruction. You find an entry in BTB, okay, this is a function call, you need to jump to 10,000. You're at address 1000, you need to jump to 10,000, and you need to return back from the function at 1004. That 1004 address is what is pushed into this particular stack within the branch predictor itself. Right. So the next time you encounter a return operation, remember the returns are never the constant, right? Returns depend on the actual register in RD. That's where your return address is, right? When you did a call, you put 1004 in RD. So when you return, you need to return to the address that was present in RD. Let's say that was X1. Right? So what the branch predictor will do is, as soon as it detects a return operation on the PC, it will pop the first address from here. So if you do 4 function calls, for example, function 1, you go to function 1 and then function 1 goes to function 2, right? So function 1 will push an address 1004, function 2 will push an address 2004, function 3 will push an address 3004, right? Now when function 3 returns, the predictor will predict it correctly and say that the next PC is going to be 3004. When function 2 returns, the top of the stack is pointing to 2004, and that's where you pop 2004. And finally, when function 1 returns, you pop 1004. Right? So that's how function calls and returns can be significantly, prediction for them can be significantly optimized by using something called as return address stacks. And this is purely because of the structured nature of calls and function returns. Right? So that's why we use return address stack. Now, what are the flaws with the return address stack? Let me say that. Let's say I give you a return address stack of 8 entries. What could go wrong?
Overflow.
Correct. So if I do more than 8 function calls, nested 8 functions, then my return address stack is polluted. Right? The 9th function call, I will never be able to return correctly. Only the 9th one will work, or after a certain point, some of those function calls will not work. Right? So for example, recursion. If I have 8 depth of recursion, it works very well. Return address stack will be able to predict correctly for all the 7 times, right? Assuming the first time it's used for training. But if I have a if I have a RAS of 8, but if the recursion depth is more than 8, let's say it's 20, then it's not going to work, right? Only the first 8 transitions, 8 returns will work. After that, everything will be a misprediction by the RAS. So this was a rollback. Again, remember, this is predictions. Predictions can be true or false. Predictions are not necessarily always correct. Whenever they are wrong, the execute stage needs to revert whatever mistakes you've done. Because when you're predicting something, you are speculating and you're doing you're populating the history register with more speculation as well, right? So you need to roll back all those speculations that you performed in the PC gen stage as soon as the execute stage says that you have a branch misprediction. Also, when you have self-modifying code, you will be modifying the instruction cache, correct? So whenever you perform a fence.i, you're flushing the instruction cache, because now the same address, which was earlier a branch instruction, could now become a add operation or a mul operation, right? Because you modified the instruction region itself. So whenever you perform a fence.i instruction, you should also flush the entire branch predictor as well. Right? Otherwise, what will happen is you will end up predicting that a mul operation is a branch and you should now jump from mul to some other place, which is wrong. Right? So whenever you are flushing, whenever you perform a fence.i, you also need to clear your branch predictor as well and start training for the new code that is present. Any questions? Branch predictor. Okay, good.
Hello.
Yes.
Yeah, so intuitively, it seems that branch prediction can lead to very severe hazards.
What are the severe hazards?
As in, if the prediction is not working correctly.
So the penalty is 3 cycles, right?
3 cycles. Okay.
Yeah, so the idea is you have execute stage, which will tell you a misprediction, right? It will tell you what the misprediction, whether there was a misprediction or not. But in that time, you decoded, fetched, and generated 3 instructions, correct? So you need to flush all 3 of them and start with a new PC. That's why it's 3 cycles.
Okay.
And as the 3 cycles is assuming you have a instruction cache hit, right? So that's the minimum penalty that you pay. 3 cycles is minimum. The maximum will include, a cache miss followed by an L2 cache miss followed by 10 other things, page faults, blah blah blah, whatever happens there. But the reason you use a predictor is because nowadays the predictors are 90, 95, 96, 97% accurate. So only for 3%, if you're paying a 3 cycle penalty, that's fine.
Okay.
This prediction would happen at which stage? I think it should be decode, right? Because before that, we don't know whether it's a branch or what kind of instruction it is.
It's in the PC gen stage, right? So your BTB holds those entries. No? So whenever the execute, so on reset, everything is empty. The execute stage receives its first branch. It goes and allocates a BTB entry. By that allocation, what you're saying is this PC, the current PC is a branch, and it jumps to new PC. So the next time the same PC comes, you're going to look up this branch target buffer and say, does this PC exist in the BTB? Yes, it does. Therefore, jump to that new PC. So that's why we do it in the PC gen stage.
Okay, got that.
Excuse me, sir.
Yeah.
So could you explain again how the predictor detects if the prediction is wrong?
The predictor will not detect the prediction is wrong. The predictor will only do a prediction. The execute stage. The
Yes, sir.
execute stage is what will check whether the prediction was correct or wrong. So when the branch instruction was here, you predicted that. So let's say at PC 1000, you have a branch instruction, right? You send the branch instruction next, and the predictor said that the next it was taken, and the next address is 2000. So this branch instruction gets fetched, it gets decoded, it gets executed. Now you're also sending the prediction bits along with the branch instruction. What the execution stage will do, it will calculate what was the nature, whether the branch is actually taken. If it was taken, what was the prediction? Was the prediction also taken? If it is, then it's good. But if the actual evaluation and the prediction don't match, then the execute stage will send out a signal to all the stages before it. It'll tell the decode stage, flush out everything you're doing. Tell the fetch stage, flush out everything that you're doing, and it'll tell the PC gen stage, hey, you were wrong. You need to start from this PC. And it will go tell the predictor that, hey, you need to fix your history table as taken, or this is the actual evaluation of the prediction that you had done.
Yes, sir. Thank you.
Okay, so next is the fetch stage. Fetch stage is primarily filled with L1 caches. Now we're going to talk about caches here, and this is going to be for both instruction and data caches because they have similar architectures. The only difference is instruction caches don't have a notion of stores. Right? There is no store that can happen in instruction cache, but all other mechanisms are exactly the same. Right? Caches have 2 major components. One is the tag array and the data array. Right? I'm not going to spend too much time on caches. I mean, cache itself is going to be a very huge literature in itself. I'm just going to cover very brief level working of what we've implemented. So we have a tag array and a data array. These are set associative and write back caches. So write back means you need to maintain valid and dirty bits. Anytime you perform a load or a store, it only remains in the cache. It does not go out to memory until you perform a fence or until the line has been evicted. So whenever you get a miss in the RAMs, whenever there is a miss in the tag or data array, you send out the request to the main memory, right? The main memory is going to respond with the data. The data is written to some structure called the fill buffer. Right? Whenever there is a miss in the data, miss in the RAMs, you basically populate an entry called the fill buffer. Each entry in the fill buffer is cache line sized, right? And it can have 4 entries, 8 entries. It's all configurable. Let's say we have 8 fill buffer entries. Right? Now it's possible that the fill buffer becomes full. Right? You got 8 misses back to back, and all 8 misses ended up filling 8 different lines in the fill buffer. What do? You first stall the core, saying that, hey, my fill buffer is full. I cannot take any more requests. What you then do is you pick a line from the fill buffer head, which means the first miss that or the first line that was filled. You pick that and you write it back into the RAMs so that you get 1 entry free, and then you can resume operation. Right? And you do this continuously. Now you can be a little more opportunistic, and you can say that instead of waiting for the fill buffer to become full, whenever the core is idle, in the sense when the core is not providing a load store request, let's say the core is doing some multiplication operation, I will use those cycles to release from the fill buffer into the RAMs, right? So that I don't reach the condition of fill buffer becoming full very often. And why I shouldn't? Because I want to avoid delays on or I don't want to stall the core because of a fill buffer full. Very simple, right? Now what happens because of this release? Imagine you have 4 ways. It's possible that all 4 ways are dirty, right? They all hold valid dirty lines. When you try to write a line from the fill buffer into that set, one of those lines have to be replaced and they have to be evicted. So this is where the eviction. So evictions happen on a release, right? That is more important to remember here. Finally, you have a store buffer. A store buffer, basically, whenever you're performing a store operation, you don't directly update the memory. Right? As we will see, your memory is accessed in the memory stage, but traps are generated in the write back stage. So you don't want to speculatively update a memory, right? You want to make sure that the memory changes only when the instruction is ready to commit, not otherwise. Right? So until the memory stage, all instructions are speculative, right? They have not actually changed the architectural state or registers, and it's possible that a trap from the write back stage can destroy everything, and you need to roll things back. So what we do is, as soon as a store request comes, we update a store buffer which holds the bytes of the line that need to be updated and the value with which they need to be updated with. Right? So a store buffer is very small, typically 2 or 3 entries. You don't need more than that. And it simply holds information about which line in the fill buffer should get updated with what value, or which bytes of a line in the fill buffer need to be updated and with what value. Remember, all stores only happen to a line in the fill buffer. So what happens on a store if it's a direct hit in the RAMs? If you get a store request from the core and you see that the line is present in the RAMs, you move that line into the fill buffer and you invalidate it from the RAMs and you allocate a store buffer entry. Right? Now, when the instruction in the pipeline reaches the write back stage, it's going to send something called a commit signal. It's going to say, hey, the store is ready to commit. The entry from the store buffer head performs the change in the fill buffer and removes that entry, which means the store has finished. And now a regular operation, whenever the fill buffer has an opportunity to write to RAMs, it does, or whenever it is full, it performs a release operation. Right? So the reason we've done this is the major constraint that we have taken here is we've kept the SRAMs as a single read-write port memories. Right? What it means is you have only one port to either perform a read or a write. And SRAMs are something that comes from your fab. These are things that your manufacturing plant will give you as PDKs or physical design kits. It's going to give you SRAM cells. And single read-write port memories are the tiniest and the fastest memories possible. Right? As soon as you add more ports, either the area increases or performance decreases, right? A single read-write port is the fastest SRAM technology that you can get for a particular node. And in order to leverage that, we have come up with this particular fill buffer plus store buffer and release architecture that is there. Any questions?
So can you
go ahead.
So can you explain when the data is fed from the fill buffer back into the SRAM, where does it go after that?
It sits in the SRAM. SRAM is, I mean, these are RAMs which are part of the cache itself. These are not external memory. Right? This is all the entire cache. Right? Cache will have a tag array and data array. You implement those arrays as RAMs, not as array of registers. So the fill buffer will know that this line is supposed to go to set 4 and line 3 or something, right? The replacement strategy will tell you within set 4 which line to be replaced, and you will simply write those values. Now, whenever you get a fence operation, then all of these dirty lines in the SRAM arrays will be evicted out into the main memory, and this becomes completely empty.
Okay, thank you, sir.
So if you go through the read the docs documentation from slide 2, I guess, it has a very detailed explanation of how the caches work, right? Complete text and graphics and everything is there. Memory management unit. So when you have virtualization, you have something to translate virtualization. So anyone knows what virtualization is? Let me start there first. Virtual memory.
Mapping logical addresses to physical spaces.
Yeah. So the idea is you have, let's say, X amount of memory, and you multiplex that in your RAMs. So in such a way that all your processes believe that they all have access to the X amount of RAM, right? So if it's 2 GB RAM, your virtualization will allow you to have virtual and physical addresses where multiple virtual addresses, and depending on the processes, can map to the same physical address. Right. So that's virtualization. And in order to perform the translation, give me 1 minute. Yeah, so in order to perform that translation, there is a paging mechanism. You have page tables and all of that. Cache is usually a cache of the memory. A TLB is a cache of the page table section alone, right? So it says that if I get a virtual address of this region, then I know this is going to be my physical address. It quickly tells you what the physical address is instead of going to the actual page table in memory and figuring it out. TLBs are a cache to the page table. So you can directly look up what your virtual address is. If it is present in the TLB, you know what the physical address translation is, right? So this is the, the mechanisms and the permissions, and each page table entry will have various types of permissions. It will tell you whether it's readable, writable, executable, whether supervisor has access to it, user has access to it, whether it's a global page or has it been accessed before, all sorts of different things, right? So the supervisor privilege spec will tell you, will indicate all those permissions and all those setup of the page tables. The TLBs are nothing but a fully associative lookup. You get a virtual address, you check whether the mapping of this address exists in the TLB. If it does, then the TLB tells you what the physical address is, and you start accessing the cache and go forward. If the TLB is a miss, you go to something called the page table walk, right? And the page table walk will then access memories and tell you what the actual page translation is. So there are two ways to implement TLBs. One is the checks are performed in parallel with a cache lookup. So when you get a virtual address, you send it to the TLB, which will give you the physical address in the next cycle. And similarly, when your caches are implemented at RAMs, RAM usually take 2 cycles for a read. So the first cycle you latch the address, and the next cycle you can read the values from the SRAMs, right? So that way you can sort of parallelize the access. You can access the RAMs and the TLB simultaneously, so that in the second cycle, you can perform the tag match between the physical address from the TLB and the tag array of the caches. You can also have, so typically we implement a fully associative TLBs, and there is a limit to the size of those TLBs. You can't exceed 32 or 64 without compromising on performance. But if you wanted to really have very large number of TLBs, you can go for set indexed versions. Now, in RISC-V, there are different page sizes that are available. You have 4 kilobytes, 2 megabytes, and 1 gigabyte page sizes. And if you want to do indexed TLBs, you need to maintain a TLB for each of those types of sizes. So whenever you encounter a 1 gigabyte page, you have to store it in this particular TLB. All 2 megabyte pages will be mapped here, and all 4 kilobyte pages will be mapped here. Right? Now, as you can see, we sort of indicate that all the 4 kilobyte TLB should be much larger in number of entries as compared to 2 megabyte, and 1 gigabyte can be really small. The reason is if your operating system is using 4 kilobyte pages, then it's going to require a many number of pages to map the same amount of physical space. Right? So if I have 4 GB of memory, I only need 4 1 gigabyte pages, right? So I can have maximum of 4 entries only, and maybe slightly higher number of 2 megabyte and significantly higher number of 4 kilobyte pages, right? So I access all of them simultaneously. Only one of them will be a hit, and whichever one is the highest page, which is a hit, that provides the physical address to me. Is that clear? Any questions? Okay, moving forward. I'm skipping the compressed part because this is a little bit of a distraction at this point, considering the time limit that we have. The next stage is the decode stage. So once the instruction cache gives you the instruction, you send it off to the decode stage. It's very simple. The decoder is supposed to give you all the fields of interest. It's going to create the decode, the immediate fields. It's going to access the register files. The register files will have 2 read ports and 1 write port. 2 read ports to read the 2 RS1, RS2 operands, and 1 write port where it writes into the, from the write back stage, you write the result into. Depending on the instructions, it's also going to decode the instruction into some high-level functions, like is it an ALU operation, like the arithmetic or logic operations? Is it a memory operation? Is it a branch operation? Is it a CSR operation, or it's a jump instruction, and all sorts of things? So we are not decoding at a very granular level, at an instruction level, but in terms of functional units present in the execution stage, we want to decode which of those functional units will process this particular instruction. So this basically tells you functional unit type rather than instruction type. We also extract some of the meta fields, like what are the func3, func7, because the decoding of this will happen in the execute stage, right? When you say this is an ALU operation with this func3, the ALU will use the func3 to decide whether it's going to be an add or a subtract or what operations. So this is a quick example of the blue spec code that you will find on the repository for Chromite. As you can see, right, for each bit 0, you can build a 3:2 or a 2:1 mux of sorts, right? So bit 0, this is the default value. And if it is an S type, you get instruction 7. Else, if it's a B type, U type, or J type, bit 0 is set to 0. So you can infer the 3:1 mux for bit 0 here, and so on, right? So this is just an indication of why those jumbling immediates, how do they correlate to actual simple hardware.
Excuse me.
Yeah.
How is BlueSpec better or worse over normal Verilog code? I mean, what is the advantage it provides over Verilog or VHDL?
So BlueSpec gives you very high level of abstraction. You don't work at a gate level or a register level. You work more of a module level. You can build parameterizations, significantly highly parameterized modules. It takes care of a lot of automation of race conditions. And if you want to build a multi-resource sort of a design, let's say you have one memory and you have 3 or 4 consumers or design units which are consuming from memory, right? So how do you schedule accesses? In Verilog, you'll have to write all of that glue logic. BlueSpec will automate that glue logic creation of if resource 1 is accessing memory, then resource 2, 3, and 4 will be blocked. All of those conditions become very implicitly defined by BlueSpec itself. So it gives you a strong library like FIFOs, RAMs, registers, shift operations, a lot of abstract functions and modules which are already present. And the notion of atomic rules. So it says that, in this is what is supposed to happen in one clock cycle. And that atomicity of that rule ensures that there are no race conditions, that there are no unsynthesizable or combinational delays, combination cycles that are introduced in our design.
Okay.
Yeah, someone has a question. Okay, moving forward, you can also decode a few exceptions here. For example, illegal instructions. If you identify an instruction which is not present in the encoding space, you tag it as an illegal exception. If it is a CSR operation and you're accessing a CSR which does not exist in the memory space in your implementation, you again generate. Or if you're trying to write to a read-only CSR, or if you're in the user application domain and you're trying to access the machine CSR, all of those will cause illegal exceptions. You can also detect breakpoint and eCall exceptions. Interrupts are also detected in the decode stage. You check for any external timer or software interrupts that are generated in the system. And from here on itself, you can sort of tag an instruction as an interrupt and move forward instead of detecting them in the write back stage. The next module that we're going to look at is scoreboarding. Scoreboarding is a mechanism of doing operand forwarding of sorts, or bypass logics, right? So there are instructions in the pipeline which have not yet committed, which hold the results, which have finished execution but not committed. They hold the results on which the newer instructions depend on, right? So instead of having the newer instructions wait, or even to detect whether the newer instructions depend on an instruction in the pipeline, you need some mechanisms to tell you that, and scoreboarding is where that comes in. Right? So scoreboarding basically has a vector of 1 bit, or you can have different ways of implementing scoreboards. It basically says this pipeline stage has this instruction with this result of this register, and if a newer instruction wants that as an operand, it can either read from a intermediate ISB in interstage buffer, or it can stall until that instruction has committed. Right. So we have both those mechanisms in Chromite. You can choose that configuration whether you want scoreboarding or you want to stall completely. Both of those mechanisms exist. The major hazards that scoreboarding will actually address is the read after write and write after write. Those are the two important hazards that scoreboardings will help you alleviate. So there are two mechanisms to implement scoreboarding. You can have for each instruction in pipeline, check its RD, right? So if you're in the execute stage and you have 2 more stages ahead of you, you need to check both of those stages, whether any of the instructions present there have an RD equivalent to your operand. That is one mechanism. So you need to do this 5-bit comparison. Or what you can do is in your register file, you can have 1 more bit extended against every register. And that bit will tell you whether an instruction exists in the pipe, which is going to update this particular register. And based on that information, you can make a decision of either to stall or to wait for the bypass to happen, or wait for it to commit. Any one of those things can happen. The next is the execution stage. The most important part of the execution stage is the ALU. It's one of the most important in terms of area because it includes the adders, subtractors, shifters, and we need to take really good care in terms of building this ALU. So let's look at all the instructions that will be executed by this particular ALU, right? You have branch instructions which require operand 1 and operand 2, and you need an adder to compute the actual branch, right? So PC plus immediate offset. JL is going to require PC plus immediate offset and the next PC, that is PC plus 4, which needs to be written into RD. Similarly, JLR, you're going to have operand 1 plus immediate offset. Load requires only operand 1 and offset. Store requires operand 1, operand 2, and the offset. AUI PC requires PC and immediate offset. Immediate operations will require only operand 1 and the immediate field, and register operations will require 2 operands, right? Operand 1, operand 2 from the register file. So these are all the sources of information or sources of operands that your ALU will have to get access to so that it can perform necessary operations. So if you were to build a table and say that if I have 4 inputs and this is how I'm going to do, this is how I'm going to mux the different inputs into the 4 inputs of the ALU. Sorry. So for the branch, the 2 operand comparisons will go through in1 and in2, and in3 will have PC and immediate. Similarly, in1 will have PC and the value constant 4, and in3 will get PC plus immediate, right? And so on, right? So this table, what we've basically done is in3 and in4 basically have the inputs that are used to calculate an effective address. Whether it's a branch instruction or it's a JL or a JLR or a load or a store operation, in3 plus in4 will tell you the effective address either because of a branch or the effective memory address, right? So that becomes a pipeline of its own, that becomes a computation of its own. In1 and in2 are typically where you will perform all the other operations of shift left, comparisons, and all of that, or additions, subtractions, depending on the ALU. This particular example basically tells you how you can perform comparisons using the adder itself. You don't need to do a comparator. Comparators are costly because they will involve XOR operations, and the comparators themselves are slightly costlier. What you can instead do is you can use the adder which already exists because you have an add operation to support. You can use the output of those adders along with some minimal checks in order to detect equal, greater than, or unsigned operations for the branches. You don't need separate comparators. You can overload the adders itself in order to perform those comparison operations. So shifts, you will have to build a shifter. What we do is we implement only a right shifter. For shift left, what we do is we reverse the bits, do a right shift, and reverse it back. Right now, reversing bits is no hardware because you just have to mux the bits. Bit 0 becomes bit 31, bit 1 becomes bit 30, and bit 2 becomes bit 29, and so on. So you just have a 1-bit mux which is present, which is much lower overhead than putting in a new left shift module, right? So we have a 60, or for a 64-bit core, we implement a 65-bit signed shifter. And the same shifter, if you reverse the bits at the inputs and outputs, you can use it as a left shift as well. You can also detect some exceptions within the ALU. So when you're doing memory operation address calculations or branch address calculations, you can check for misaligned operations there itself. So if you go through all those requirements of adders, subtractors, shifters, XORs, this is what you would end up with. This will require less than 400 LUTs on an Arctic 7 FPGA. There are mechanisms to increase this, decrease this further, but you will have to pay a performance penalty or improve performance and increase the LUT utilizations as well. Other than that, as we said, we will also be doing prediction calculation within the execution stage. So the ALU will tell you this is the address of the next PC, and you will check whether the PC in the previous pipeline is it the same or not. And if it's not, that's when you generate a misprediction and you flush the entire pipeline. You can also have multi-cycle operations. For example, if you perform multiplications or floating point operations, they start in the execute stage, but they will take significantly longer number of times, maybe 8 cycles. For example, division takes 64 cycles and more. And only then the results are available in the memory stage. The memory stage is very straightforward. We've already seen the data cache. The address generated in the execution stage is sent off to the cache, and the cache responds back to the memory stage with either a hit or an exception that it would have detected during the operation. So PT walk, on a miss of the TLB, you do a page table walk. There is a module called, I don't think I've shown it here. Yeah. So there's a module called the page table walk. So whenever you have a TLB miss, you go and access the physical page table, which is in the memory, and you perform the physical translation, virtual to physical translation, and then you populate the TLB. So all page table walks accesses to the memory happens through the cache, right? So remember that, because the pages could exist within the cache. The updated pages that you see may exist within the cache, and you don't have to go all the way to memory. So whenever you get a TLB miss, your page table walk will again access the cache, and the cache may generate a miss and then go to memory. But if it's present in the cache, then the page table walks become really fast. And finally, you have the write back stage. So the CSR files are maintained here. You perform all CSR operations here. In case of store operations, you send a commit signal to the decache store buffer, as we saw earlier. In case of non-cacheable stores or loads, you initiate the transactions on the bus in the write back state. You don't want to do them speculatively early on. So only when the store operations reach the write back stage and you realize they are non-cacheable, you start performing those IO operations in the write back stage. If you've detected any traps, the write back stage generates a trap vector and flushes the entire pipeline and tells you where to start accessing the trap handler from. And regular operations will simply update the register file. So as we've seen, there are basically two places in the pipeline where a change of PC can be initiated, either from the execution stage because of a misprediction, or from the write back stage because of a trap. Now, how are you going to flush a pipeline? So flush a pipeline means everything before that stage needs to be dropped and a fresh set of execution needs to happen, right? So a question to you guys is, let's say from the execute stage, you get a misprediction, you need to flush the decode stage, fetch stage, and the PC gen stage. How do you do that in hardware? What would you implement to flush things?
A single control signal which would tell all the previous stages that the whatever data or instruction it has, it needs to be flushed out.
Okay. So you're going to put an if condition on all the stages saying if I get this signal, but you also have these ISBs, right? Interstage buffers. So in the current stage, decode may say, okay, drop it, but what happens to the instructions that are already decoded and put up in this queue here? The instruction interstage buffers can be much
We
longer.
can stall the pipeline, do the necessary changes to all the values, and then allow the pipeline to resume.
That's going to take a lot of latency, no? Then your misprediction latency will be so huge. So let's say I put 10 entries here. You're going to spend 10 cycles just removing them. Correct.
Is it possible to instead of dropping anything, whatever we have in that pipeline stage, we will just not allow it to execute. So we will. So in this case, we also don't need to drop anything and send signals or something like that. I mean, just stall the execution stage. Sorry.
So how do you prevent it from executing?
Just switch off the execution state for certain amount of cycles.
Mm-hmm. So yeah, I mean you're there. So what we do is we have a bit called an epoch bit in all the stages, previous stages, right? So execute, decode, fetch, all of them has an epoch bit. The reset value of the epoch bit is 0. It's just a 1-bit register. Now, whenever execution stage says that it's a misprediction, you go and flip this bit. in all the stages, right? Now, whenever an instruction is fetched, you associate the instruction with the epoch bit under which it was fetched, right? So initially, when the first instruction came in, the epoch bit was 0. So instruction 1 has an epoch bit 0 associated with it all throughout the pipeline. When the stage's epoch bit flips, right? So in each stage, you're going to check, hey, what is my current epoch bit? And what is the epoch under which this particular instruction was fetched? If they match, only then perform the relevant operations of that stage. Else, just drop that particular instruction. Don't perform any operations in any of those stages. Right? So even if I was fetching, let's say I've fetched some instructions, kept it here with fetch epoch of 0, and the epoch bit in the decode stage flips, right? It becomes 1. So as and when an instruction comes here, the decode stage is first going to check, is my epoch bit equal to the current epoch bit of the stage? If not, don't even decode that instruction, just drop it. Right? Only when it encounters a new instruction whose epoch was 1, it decodes it and sends it to the execution stage. So this becomes a very lightweight operation. You basically just have 1 bit in each stage for the epoch of the execution stage, for any misprediction that execution stage can detect. Similarly, we also know that write back can generate a redirection. So for all stages before the write back, we associate a write back epoch for every stage before it. Right? So the fetch stage will have 1 epoch bit which will indicate the write back epoch, and the second epoch bit which will indicate the execute epoch. And only execute can flip the red bits, and only write back can flip the blue bits if there is a redirection. So the whole idea of flushing a pipeline becomes very simple. It ends up being just 5 bits or 5 registers, or here 8 registers across the pipeline. And you just have to compare these 1-bit registers to check whether you need to execute or drop that particular instruction from a particular stage. Okay, good. So I've overshot in time, but I've finished the architecture of Chromite today. We will be having a session at 2:30 on a lab session. So one of my colleagues at Encore, Pawan, is going to walk you through on how to install, how to compile assembly programs with RISC-V, how do you run it on Spike, instruction set simulator, and all those things. So if you do have the tools installed, please be available at 2:30. And thank you. And I'll be available for questions if there are any.
Thank you, sir.
Thanks.
Thank you,
Thanks,
sir.
sir.
If you have troubles in installation, is it possible to come at 2:15 or 2 o'clock?